Hi, this is Robert Quimby, and I'm going to tell you about the Lomb-Scargle Periodogram. So as an astronomer, you may go out and measure a signal, maybe the brightness of a star over some time, and you may look at the signal and notice that it's not constant, that there's actually some fluctuations in the signal over time. You might want to quantify those fluctuations and see if this is a periodic signal. So what you want to do is go from the magnitude of the star over time to the power in each frequency. So one way to do this is to calculate the Lomb-Scargle Periodogram, and that'll give you this information here, the frequency, the power versus frequency. And then using this, you can go on to figure out what the period of the signal is. So in this tutorial, we're going to begin by just reviewing Fourier decomposition. I'll remind you that you can take any periodic signal and you can represent that with the sum of a series of sine and cosine terms. We're going to actually do that. We're going to go through this exercise and create a signal just using sine and cosine terms. And then we're going to do the reverse process. We're going to take the signal we've generated and we're going to deconstruct it and find what the amplitudes of each one of those sinusoidal terms is. This is essentially what the Lomb-Scargle Periodogram does. And so we're going to actually then use the Lomb-Scargle Periodogram to find the period of a real astrophysical signal. As always, this is going to be just a quick introduction to the topic. If you want to know more, there is a nice paper by Jake van der Plas that'll go into much more detail on this. I suggest you check that out. So hopefully if you've seen this before in your math classes, you can take any periodic function and you can represent it as the sum of cosine and sine terms. Each one of these is going to have a slightly different frequency and they're going to have different amplitudes. But by adding up these sine and cosine terms, you can represent any arbitrary periodic function. So for example, we can look at the decomposition of triangle waves. So a triangle wave is something that starts off and goes straight up and then straight down and straight up and then straight down like that. That's a triangle wave. So it's similar to a sine wave, but it's not as curvy. So how do we go from these curvy sine waves to these linear changes? Well, all we have to do is actually just take the sine terms, we don't even need the cosine terms, find the appropriate amplitudes for the appropriate frequencies, add them all together, and we'll get a triangle wave. So we can go ahead and code this up in Python. So what we're going to do is we're going to just add each one of these sine waves in this list. We're going to keep track of that. We're going to convert it to an array at the end. And so we're just going to go through each one of these n terms. We just need the odd terms as well. So for the odd terms, we're going to record the amplitude, and that's just going to be -1 to the power of n-1 divided by 2. And that's all going to be divided by n squared. So that's going to be the amplitude of each one of our sine waves. We also need to record the frequency here. That's just going to be n divided by p here. So n divided by our period. And then we can create a sine wave at the appropriate frequency, multiply it by the appropriate amplitude, and we'll keep track of that in our components. So now we can test out our function. We'll just create a bunch of test times, just between 0 and 3. I have 1,000 different points where we'll calculate what the signal should be at each one of those. So we're going to get the components for each one of those terms. So we're going to give it the times where we want it to be calculated. And we'll pick how many terms we want. Let's start with, say, 2 terms. And then for each one of those sine waves that we're going to generate, we're just going to plot them. Start with that. So here we are. So you can see the first term here, it's the blue one here. We got just a nice sine wave. And then the second order term is just a higher frequency sine wave with a lower amplitude. So let's add another term here. And you can see what's happening here. So each time we add a term, it has a peak at the same spot. It's always going to peak right here. It's always going to have a trough right here and so on. And so what this is going to do is it's going to be, if we add these together, it's going to lift this peak up. And over time, these waves are going to get more and more narrow. So it's going to end up giving us a very, very fine point here on our peak and a fine point on the trough. And then on the sides here, what we're doing is we're kind of taking out some of the curve in this here. So we're subtracting a little bit here and a little bit there to make this in more of a straight line. So if we actually just look at the sum of all these terms, that's the wave that we want to generate here. That's our signal. And that's just going to be our components, the sum of those. And we're just going to go over axis 0 so that we don't want to sum over time. We want to keep all those times. We're just summing basically vertically in this plot. And we'll take that signal and we can plot that as well. We'll make these lines black, and we'll put in a bolder line. We'll make the line weight 3, and we'll plot this. And there we go. So this is the line that we've generated with just 3 terms, just 3 sinusoidal terms. We add those together, and we get this black line here. And you can see what happens now as we add more terms. The peak gets a little bit sharper, and this line gets a little less wavy. And so we can have 5 terms, we can add 6 terms. And as we do that, you can see every time we're getting more and more linear here and more peaked here. Eventually, you can add a whole bunch of terms. And you can see what that does. It gives you something that's very, very close to a triangle wave. And of course, in the limit that we have an infinite number of terms, it's exactly a triangle wave. But just with 6 terms, we actually get pretty darn close to a triangle wave. So we can see from these components that the first sine wave we made, this blue curve here, is the most important in defining this triangle wave. All these other terms, they're adding to this, they're making it closer and closer to a triangle wave. But most of the power is actually in this first term here. So let's explore that now. We're going to take a look at what those amplitudes are for each one of our sine waves. So again, these are the BN terms. We're going to keep track of that, and the frequencies. Just going to use 6 terms here. Stick with a period of 1. And then we're going to add all the terms. And I'm going to keep track of the even ones as well. So if we have an even term, we're just going to set the amplitude to 0. If an odd term, we're going to set the amplitude as appropriate for a triangle wave. And then we're going to record all these amplitudes and frequencies and turn those into arrays so we can work with them. So I'll run that. And now what we can do is we can just make a simple plot. We're going to make a bar plot here, just showing for each frequency what is the amplitude. And there we have it. So we can see, again, we already knew this visually just looking at the plot, but that first sine wave has a much larger amplitude than anything else. It is important to note that some of these amplitudes are negative. So that second term has a negative amplitude, and then goes positive, negative. It's got this odd even effect here. So often what we want to know is what's the power in each one of these terms. Not just what the amplitude is, but what's the power. And so to calculate that, all we need to do is we can just square each one of these terms. So let's go ahead and do that. Again, we're going to plot our frequency. And now we're going to do the power. So we're going to take our BN amplitudes and just square those. And this will give us the power. So we can see here that most of the power, again, is in that first term, and then it decays pretty quickly after that. So I'm going to put this on a log scale. Just to make it a little bit more visible what's going on here. Now you can see these other terms peeking up here. But again, it's a log scale now. So these are much less power in each one of these terms than in this first sine wave. So hopefully this reminds you that you can take a series of sine and cosine waves and you can put them together and you can make a triangle wave. But that's not the case that you're usually working with in astronomy. Usually you're given some signal and you want to do the reverse process. You want to figure out what the power is in each one of its frequency components. So let's start now with this signal. So we've sampled a triangle wave at discrete points over time. And what we want to do is just given these data, just given this signal at these times, we want to reconstruct the components of the triangle wave. And we'll see if we can get exactly what we put in, because we know what we put in to make this triangle wave. Let's see if we can recover those just given these data points here. So there's different ways we can approach this problem, but from what we've just motivated, one way that you can think about this is that we can actually just go and try and fit sine waves of different frequencies to these data and see how well the sine waves fit. And if the sine wave is a good fit at some frequency, then we can say, well, that frequency probably has a lot of power in this signal. And if it's a poor fit, then we can say, well, there's probably not much power for that particular frequency we picked. So all we have to do is pick a whole bunch of different frequencies, do a fit, maybe a least squares fit, to figure out what the best fit amplitude and phase are, and then record how well each one of those fits represents the data, And then we can use that to reconstruct the amplitudes of the terms in the signal. So to the data we have data y data points sampled at times t, and all we need to do is fit a function like this. We just can use any sine sort. I'm going to use a cosine here. You can use a sine if you want. They're all just a difference of a phase shift. And we're just by adding these terms together, we can fit for the amplitudes and phases here and figure out what the best fit values are, and then ultimately determine if that's a good fit to the data. So if you look at the way I've set this problem up here, you may immediately notice that the two parameters we have, a and phi here, are not linear in this equation. So we could use some nonlinear least squares fitting to figure out what these terms are, but it turns out there's a nice trig identity that will allow us to do just straight linear least squares fitting. So all we have to do is just recast this equation in a form that is linear in a and phi, and the way to do that is with a trig identity. So there's an identity that a cosine of some angle plus some phase is just equal to the cosine of that angle plus the sine of that angle with some different weights than we started out with. So this is very handy to know. All we have to do to fit the problem at hand is we make the substitution that theta is equal to 2 pi times the frequency times the time. And then note that we can recover what we want. We want the amplitude and the phase information for each one of the models that we're going to fit. And we can get those in terms of the B and C values that we're going to actually fit for. So the A amplitude is just the hypotenuse of B and C. And the phase, phi, is just the arctangent of C over B. So with this trig identity in place, we can go ahead and set up our equations for a least squares solution. So again, we have our observed data points, our y's, and we'll just set that up in a column matrix. And then we have what we're going to calculate. We're going to define y is going to be equal to b cosine theta plus c sine theta. So we have a bunch of cosine and sine terms for each given frequency at each time, multiplied by our amplitudes b and c, and then we can fit for b and c. So let's go ahead and code this up in Python. First thing we should do is figure out what frequencies do we want to test. We can test any frequencies we want, but we kind of already know we should just be testing integers because that's how we set up the problem. So we'll just make it easy. Just do numpy a range of 11 different values. We want to start with 1, so we're going to add 1 to that. And then we'll set up our y matrix. So this is, again, the signal at each observed time. So that's just going to be the value for value in our signal. And again, I put it in square brackets here because we want a list of lists so we can make a numpy column matrix. And then we'll set up the amplitudes that we're going to fit for and the phases we're going to fit for. And then for each frequency we're going to test, we're going to set up our thetas, right, for each time. And then we're going to create our X matrix so we can solve y equals x times p. And so this is the matrix that has the cosine theta and the sine theta terms for each theta in thetas. So then we solve this as always. We do our matrix algebra here to solve for p. And then from P, we can extract the parameters B and C that we just fit for, and then we can convert those to A and phi using those trig identities that we just discussed. And so at the end of this, we're just going to take those A values, convert them into numpy arrays, and the phi's and convert those to numpy arrays, and we'll have our best fit values. So I'm going to run this, and it runs pretty quick. And so now, for each one of the frequencies we tested, we have the best fit amplitude and phase. So let's make a plot now to see what this looks like. Let's first start with a bar plot like we showed before, just the frequencies that we know are important and the amplitudes that we assigned when we created that triangular wave. So that looks like this. We saw this before. And now let's add to this a bar plot with the frequencies we tested and the amplitudes that we found, the best fit amplitudes squared. And we're going to go ahead and normalize these to the maximum just so we get 1 here in the first term. I'm going to plot this with just hatches with red hashes. So we can overlay that. And there we are. So you can see just by going through and testing these different frequencies, we've actually done a great job of recovering the power in the model that we constructed. In fact, they're identical matches. Up to the scaling factor, we have identical values in each one of these odd terms. And we have a little bit of power in these even terms. You'll notice creeping up here. But remember, this is a log scale here. This is 10 to the minus 29 here. So there's very, very little power that we're detecting in these. And so otherwise, we've actually succeeded in taking the signal, just the measured values over time, and converting that back into power at each frequency. So this is very close to what the Lomb-Scargle process is, but there is actually one additional twist. So here we're just fitting and we're showing what the best fit parameters are for the amplitudes squared for each one of the sine waves we've tested. We didn't say anything about how well they fit. So that's actually one further step that is done in the Lomb-Scargle process. And that is for each fit that you run, you actually calculate a chi-squared value, and you use that to determine the relative power in each one of those frequencies. So we're going to go ahead and do this. We're going to set up for chi-squared fitting. So we're going to have a model, which is just those two terms, the amplitude and the phi. And the model, again, is just the amplitude times cosine of our angle plus some phase phi. And then to evaluate the chi-square, all we have to do is calculate the predicted model values at each one of these times, and then compare that to the values that we actually observe, looking at the residual, squaring that, and taking the sum of the square of the residuals as our chi-square value. If we did have uncertainties, we could also divide these values here, this residual, by the uncertainties. But in this test case, at least, there's no uncertainty, so we're not going to worry about that. We're just going to define our chi-square this way. And now we can test this out. So for each one of these frequencies that we've done our fitting at, we can go ahead and calculate what the chi-squared is. We just have to give it the best fit model parameters at each one of those steps. So this is the ith A value and the ith phi value. Those are our parameters, our best fit parameters. And these are the times that we sampled at and the frequencies at that ith bin and the signal that was observed. So we'll append all those chi-squared values and convert it into a NumPy array. We have our chi-squares now. So the last thing we need to do is to convert these chi-squared values that we've calculated into a power. And the way we can do this is we can compare these chi-squared values to the chi-square we would get for a constant signal. So that would be equivalent to taking these models that we fit and just setting all the amplitudes to 0, just so we have a constant value over time. But our models have more flexibility in them. And so that means that these models should always do better than this simple model of just a constant signal over time. So by comparing against this kind of reference model here, we can get an idea for the power in each one of our amplitudes. So to define this reference chi-squared value, we're just going to calculate a chi-squared for a constant, so it's just the NumPy sum of the squares of the residuals, that's our signal, minus this constant term, which I'm going to set to NumPy mean of our signal, and that's all going to be squared. So that's our reference chi-squared value. And then to calculate the power, we just take our reference value and subtract off the values we calculate for our best fits. And there's different choices of how you can kind of normalize this here. A popular choice is to just divide by the chi-squared 0, by this reference chi-squared value. And that'll give you the power for each one of your frequencies. So let's go back to this plot that we had before, where we were looking at different frequencies and looking at the power in each one of those. So far, we've not actually been plotting the power, we've just been plotting the amplitudes squared. So the blue is the original and the red is our best fits. Let's see what happens when we add the chi-squares to this. So we're going to plot this with hashes going the other way in black. And there we have it. So other than a tiny scaling factor, you can see that we've reproduced the amplitudes in each one of the frequencies with power. And now this chi-squared value, actually we have zeros here in the even terms, which is good. So we now have what's called the Lomb-Scargle Periodogram for this signal, the power at each frequency. So that's great for test data. Why don't we try something real? So this is real data in this var file for a target in the sky. We've got the modified Julian dates, magnitudes, uncertainties, and a photometry flag there for this. And so we're going to just pull out those times and the signal and plot those. And this is what we get. So this is the magnitude of a star over some time. And you can see there's some fluctuations in here. And if we actually zoomed in, we can see that this isn't just random noise here. Let's see, go to 7424 and 57428. Zoom in a bit here. You can see that there is actually a signal going up and down in here, maybe a few times per day. So let's now figure out what the period of this is, just based on these data that we have. To make things a little bit easier, I'm just going to start by subtracting off the average value of the magnitude. Okay, so now we got numbers that are closer to 0 here. And then all we have to do is essentially just what we did before. We start by choosing what frequencies we want to evaluate the power at. And for this time, let's do a whole bunch of frequencies. So we'll do the NumPy linspace, and we'll span the range we think is important. It looks like there's variations over at least once per day, maybe up to 15 times per day. And so let's pick 1,000 values evenly spaced between those two, and we'll test the power in each one of those frequencies. So then we'll set up our Y matrix just like we did before. It's a call matrix. We're going to record the amplitude squared and the chi-squared values, just so we have both to work with if we want to compare those later. And then for each frequency, we're going to do the chi-squared fit. We're going to find the best fit parameters. We're going to convert those into our amplitude and our phases, and then find the chi-square for that amplitude and phase and record that. And once we've done all this for each frequency, we're going to have our baseline case here, which is just a constant signal. So we'll look at the chi-square for a constant signal, and we'll calculate the power, the Lomb-Scargle power at each one of these frequencies. So we'll run through that. And now we can plot the power in each one of these frequencies. So instead of the simple bar graphs we did previously, now we have 1,000 values. So we're just doing a regular line plot here. And you can see that there is clear contribution from a number of different frequencies in this signal. Those all add up together and produce the signal we observe. So this is actually the Lomb-Scargle Periodogram. So that shows you how the Lomb-Scargle Periodogram is actually calculated. You don't actually have to do all these steps that we did before. You can just use the version of Lomb-Scargle that's built into Astropy. So in Astropy time series, there is a Lomb-Scargle object that we can import. And then we can use these with the data. And it's all in Astropy, so it works nicely with Astropy units. We can now define our times to be in days and our magnitudes to be in magnitudes. And we can use these, and we can calculate what the Lomb-Scargle Periodogram is for these data. Just pass it the times and the mags, and it'll give us the Lomb-Scargle Periodogram. If we want the power for this, we can just say, okay, calculate the power. And we tell it what frequencies we want it to be calculated at. And we can specify units here. So if we specify units here, we have to specify units here. So I'm just going to divide this by u.day. And then get rid of that int 1. And there we go. So you can see this is virtually identical to what we did before, because that's essentially how this is coded up in Lomb-Scargle with some minor differences. I should also add that in Lomb-Scargle, this is defined by Astropy, it also allows you to give the uncertainties in your measurements, so you can put that in there. Also, one of the key things in this process is picking what those frequencies are. And Lomb-Scargle has some tools built in to automatically pick some for you, which may be a good place to start at least. You might want to change them after you've seen what you got, but you can always start with them. So we can use the Lomb-Scargle auto power function, and that'll actually pick the frequencies for us and calculate the power at each one of those. And so that's what that looks like. So again, very similar to what we just had. It's just now we're using these uncertainties to weight the fitting, and we're calculating the frequencies that were automatically chosen. So we now know the power in each one of these frequencies that we've tested, and we can see which ones have the most power. But what you might be interested in is knowing what the period of this object is. What's the period in this signal? We have to be a little bit careful in interpreting the periodogram to get the period. We can just start with the peak frequency, the frequency with the most power in it. But we have to remember that when we're doing this fitting, when we're doing Lomb-Scargle, we're fitting sine waves, sinusoids, to the data. And sinusoids have an up term and a down term, and then go back to where they started. Your signal may have more ups and downs than a sine wave does in each period. And so because of that, you have to have some knowledge of what your astrophysical signal should be to interpret the periodogram. So let's start off by just using the frequency with the most power in it to define our period. So we'll start with 1 over the frequency that has the most power in it. And we can take this period and we'll do some phase folding here. We'll fold the times that are observed by the period we get to determine the phase, and then we'll plot this up. And there we go. So we have, looks like we have a pretty decent determination of one of the main periods, at least, for this object. But it turns out that this is not the true period for this object. Again, we're just fitting a sinusoid, so it's got to go down, and it's going to go up, and it's going to go down again, and that's all it can do. But this object turns out to be a little bit more complicated. What we're actually observing here is an eclipsing binary. And in an eclipsing binary, you have two stars. One of those stars goes in front of the other and blocks some of the light and makes the pair appear dimmer. And then it goes around, and you can see both stars again. And then the other star, the second star, eclipses the first one. And when that happens, there's another dimming in light. But those two dimming episodes are not necessarily equal, and the period includes both of those. So we need to have two dips in each one of our periods. So the true period is not this 1 over the peak frequency, it's actually twice that. So if we plot this, we can see now the actual phase-folded signal. So again, there's a primary dip in the light from when one star goes in front, and then there's a secondary eclipse where the other one is blocking. So when you're working with real astrophysical data, your signal may not be a pure sine wave, and you're going to have to keep that in mind when you're interpreting the results of your periodogram. Hopefully that gives you some idea of what you can do with the Lomb-Scargle periodogram, and enjoy.